Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon. Today it's my great pleasure to introduce Ji Sun. He's a PhD student at the University of Alberta, and he was also our intern this summer in the Embedded and Reconfigurable Computing group. So today he's going to talk about FPGAs and some non-traditional communication methods, and what that has, what implications that has for functionality and for security. So, Ji Sun.
Okay, thanks, Ken. And yes. And my topic is about the FPGA and the side communication channels. And okay, so this is my outline. First, I will talk about the motivation, and then review the kind of side channels, and then I will propose my bi-directional side channel. And finally, I will give the conclusion and the future work. So first is the motivation. So what is the side channel? The side channel is defined as any observable information emitted as a byproduct of the physical implementation of a system. And if we talk about a computer, if on a computer we also have side channels that can be heat, noise, and electromagnetic radiation and power consumptions. And what kind of application can be used? People mostly talk about those negative applications like recovery of sensitive information. That's also referred to as a side channel attack. And there's also some positive application like working as an additional communication channel, and also can be used for IC fingerprint or the watermark. So in our research, we are developed an application that's feasible for both cases, for positive or negative. And here is an example about the side channel. So here we see that it's about the recovery of the sensitive information. The attacker is trying to implant the malicious hardware into the genuine IC. And the evaluator is trying to detect this infected IC. But because the evaluator did not know the mechanism, so for him it's like a noise. But for the attacker, he knows the mechanism, so he can recover the signal. This is for the negative application. But we also can see like for another positive application, that's when the designer implanted an authentication hardware into the genuine IC. And the end user, as we suppose, like using this hardware. And we have no idea about this mechanism, but the designer can prove that the circuit that he designed. So he can protect his, for example, like IP core or copyright. So this is for the positive application on this side channel. Okay, now I want to talk a little bit about the FPGA. The FPGA stands for the Field Programmable Gate Array. And that's an integrated circuit that can be reconfigured and reprogrammed by end users. And it's controlled by internal configuration memory located loaded when power on from external flash. And there are circuit configuration files. For example, like Xilinx has the specific netlist file, but this is binary format. And also has the bitstream file that is opaque. It's a ASCII format. So it's kind of like we can hide our designed circuit in these files that's hardly to be detected. And also the IP core is widely used. And the IP core stands for the intellectual property cores. And it is a block of logic or data that is used in making a FPGA for a product. And it has the benefits about the design reusable, and also it's portable. So here I'm showing the modern FPGA design process. Here we see that the specification, first of all, we have the specification, and then we will design it by using the tools provided, for example, Xilinx, and also the IP cores that we can get maybe from the internet or provided by Xilinx. And then we will generate our final output and load it onto the package for testing. And then if the tester we passed, then we can deploy onto the final products. But in this case, we have two suspicious components involved. That's the tools and the IP cores we used. Because they are not provided by ourselves. Like tools, we can use Xilinx or Atras, and IP cores, it can be from anywhere. And in our research, we are not developing tools. So our focus is on the IP cores. And based on this scenario, that we can say that the FPGA is amenable to the side channel communications, either for the positive or for the negative cases. Okay, and now I want to talk about what's the relationship between the side channel and the FPGA applications. So far, we found the problems located on the state-of-the-art side channels is it's always unidirectional, working as a transmitter. It never receives any signals that's from outside, so we have no control on the information that's being sent out. And also mostly working for side channel attacker. We just suspect, is there any way we can use this mechanism for the positive applications? And also this last one is how to build a positive side channel applications with the mechanisms also being feasible for the negative applications. So there are 3 points we need to take care of. That's first, we need to make sure that what we designed occupy only small area. And also it's not always on. Then the third is it can be external triggered or triggered by the specific events. And based on these ideas, it defined our research topic. We want to design a novel and plausible side channel for FPGA application. And before present our proposed side channel, we want first to review the state-of-the-art side channels. So side channel is being well investigated. It can be the timing. We have the input signal in and the output. Based on this timing difference, we can detect what's happening on the FPGA. And also can be by power. Using the simple power analysis or the differential power analysis, we can measure what's happening inside. And also by the force injection, as well as the electromagnetic emanation. And there's a paper talk about this mechanism. It's published 5 years ago by using this inductive coupling to recover the signal. And also other attacks like template or multi-channel attacks. And here mostly you found like it's talking about attacks. And so our focus is on how to make the side channel both feasible for the attack, also for the positive usage. So now we'll propose our side channels that we developed. So we implemented 3 mechanisms to provide a side channel receiver. The first is the temperature sensing, the second is timing modulation, and the third is I/O pin hijacking. We try to keep the impact of the communication to be as small as possible, be feasible for the positive or the negative applications. Okay, the first is about the temperature sensing, and this is a picture showing what we set it up. On top of that, the blue one is actually the water cooling system. And below it there's the pelvic device, so we can, using the power supply to accurately control the temperature that's on the FPGA. And the idea is by building the ring oscillator in the FPGA using several LUTs serially connected, so we can have the delay line that's and its output is clocking a counter. And we also have a reference counter that's clocked by PLL. So we can make sure that the PLL counter is not changing with the temperature. Then by comparing the PLL counter with the ring oscillator counter, we can get the difference. This difference is changing by the temperature. So we know what's the relationship between the ring oscillator frequency and the temperature. So before going deeper, I want to introduce some basic background about the integrated circuit. The integrated circuit variation is affected by the PVT, we call it process voltage and temperature. And our focus is on temperature because the process and the voltage, because we are implementing on FPGA, it's hard for us to control. Only the temperature we can control it. So the temperature, the electron, and the whole mobility depends on the temperature. The mobility gets slower with the increasing temperature if the temperature hits above minus 50 degrees. And the higher, also it will causing the higher wire resistance. It increases the RC delay and slower the gate transitions. Both will increases the propagation delay. On the other side, the threshold voltage. As the FPGA has the transistors inside, it's control the gate. But this threshold voltage is changing on the other side. High temperature decreases the threshold voltage. Because the threshold voltage is lower, so we can get a higher current. It seems like better for the propagation delay. But however, generally, the mobility effect dominates, so the propagation delay increases with the increasing temperature. This means our circuit will become slower when the temperature is going to be increased. Okay, so now back to our approach for the ring oscillator. The ring oscillator is a device that consists of odd numbers of inverters that the output oscillates between two voltages. Here I show the basic graph of this three-stage ring oscillators. So the frequency of the ring oscillator is also affected by several factors. The first is the PVT that we mentioned in the last slide. But the process we cannot control, and the VDD it's also we cannot control. And the temperature, when the temperature goes high, then we know because the propagation delay is going to be increased. So we know the frequency will going down. And this is we can control. And another factor we can control is the inverter number. But for inverter number, we need additional logic. This is not what we want because we want to make the circuit as smaller as possible. So that design can be applicable for both the positive application and the negative applications. So we put our focus on the temperature. And this is the detailed implementation. The ring oscillator can be implemented in the Xilinx FPGA by using lookup table in the CLBs and also the general purpose of the interconnect. The oscillation is under the nominal PVT, the process voltage and temperature is determined by two factors, the number of LUTs and also the relative placement of the LUTs. Because the relative placement of LUTs is related with the interconnect delay. And here is the graph about the infrastructure. And we see that the left part, that's the delay loop. We have 4 LUT delays and plus the 1 LUT invert. And right part is the 2-time clock divider. And based on our testing results, we found the reset is not playing the key role. So in our detailed implementation, we removed the reset by using this structure. the reset being removed has one benefit. That's it will becoming more hidden for the users if we want to implement this as an attacker. So this is the block diagram. And from here we see that first is the offset off-chip clock. Then it will trigger the on-chip PLL. That will become our reference clock to clock the PLL counter. And if the PLL counter is equals to the FFFF, then we will reset the counter. And at the same time, we will trigger the toggle. The triggered toggle will go to this two buffers to cross the clock domain. And on the other side, on the right side, we have the ring oscillator. This ring oscillator is triggered. The ring oscillator is clocking the ring oscillator counter. And when this two buffer stage XOR come out with 1, it means one edge is detected. This edge is from the trigger toggle. Then we will say that, okay, we need to reset this. We need to reset the ring oscillator counter. But the last read of the ring oscillator counter is being recorded on this flip-flop. And this flip-flop will copy it to the FF, another flip-flop. And this is the data that we last recorded for the ring oscillator counter before the trigger toggled. So this data will be read from the chip scope. And then we can compare this by changing the temperature. We read the data in the chip scope. We can plot the relationship between the temperature and the ring oscillator frequency. And this is the test we set up. We test in the 2 LUTs, 3 LUTs, 4 LUTs, 5 LUTs, 6 and 8, 10, 14, 20 LUTs as a delay loop. And we also tested with and without reset. And tested with and without the 2 times clock divider. And plus we also tested 25 different locations across the die area. And on the right side, we show the die area. That's the 25 locations we put. It's pretty much uniformly deployed on the chip. And then we tested under the 11 temperature points. That's 10 degrees as a step from -15 to +85. And the testing results can be concluded as a reset, as what I mentioned before. It does not play the difference on the performance. So in our final stage of testing, we removed the reset. And also the 2-time clock divider, we found it's very helpful, especially for the smaller number of LUTs, because it can remove the clock jitter and make the counter read consistent. The structure with a LUT number lower than 5 are not feasible. As the reason, I guess, is because the LUT delay is longer than a wire delay. So it's causing the LUT output, the ring oscillator output cannot be full scale. And this will causing the clock jitter on the following counter. And the counter read is decreasing with increasing temperature consistently if the LUT number is higher than 5. And the process variation makes counter reads from 25 different locations a little bit different. And here I want to mention that we are very interested in the 6 LUTs. The reason is this can give us very good testing results, and also the 6 LUTs, because it's using just 7 LUTs total, it can fit onto one CLB, and it can occupy the minimum area on the FPGA. That's the CLB. We see that it can locate all the LUTs onto one CLB. And this is the results. From the results, we see the x-axis is the temperature, and the y-axis is the counter read. And each temperature has one dot. Like this stands for the temperature minus 15, and temperature minus 5, 5, 15, and go on. And also we plot like a candle plot using the maximum, minimum, and the mean and the median. We can see that like this one, the top one will be max, and this can be minimum, and the mean and the median. It seems like this reading is very relatively consistent, and the results is we can see that for different temperatures, there's no overlap. So it means we can make this maybe higher resolution for the detail application. And so based on that, we get the estimated bandwidth. So first, the bandwidth which we thought we should be able to detect the variance down to the 0.004% at 1.1 gigahertz. And based on the testing results and some data analysis, it seems we can achieve like a 0.1 degree change from minus 40 to plus 100 degrees. And if the chip die can be divided into 4 temperature regions, we can have 4 channels available. And this can give us very good bandwidth. The bandwidth depends on sample rate times the modulation and the number of channels. So we will demo that the bandwidth is because this is we're using very simple mechanism, so we can demo for 0.5 bit per second. But we estimated the maximum can be hit 1.9 megabits per second. And there's one concern from me, not from me, from Xilinx. From one concern I found from like claim from Xilinx. They saying that this is the principal engineer, and he says in vertex 5 the speed of the fabric is basically flat from minus 40 to plus 10. But based on what we found, it's actually the temperature dominated the speed of the fabric. So I don't know what's wrong. But I guess we proved this statement is at least suspicious. Okay, and now is the demo. And this is I already loaded the bitstream onto the chip, and with the fan on it, it should working on the some kind of temperature, stable temperature. And we see that it's showing lock. And if I remove this fan for a while with the heatsink for a while, you should be able to see that lock being opened. So now it's opened. And if I put it back, it will get locked again. The reason is because the frequency changed. And this frequency causing the counter read getting changed. And we first record the nominal counter read when this start. And then we were comparing this nominal read with the current read. If it's bigger than, now we set as like 5%. If the difference is bigger than 5%, then we're getting triggered embedded circuit to change the picture. So from here, we can conclude that with the LUT number greater than 5, we can get a pretty consistent counter read. And from testing results, it can be concluded that 10-degree resolution is feasible. And the higher LUT number, even 0.1 degree resolution is possible. So this gives us the estimated theoretical bandwidth to be 1.9 megabits per second. Also, differential modulation can be implemented as a way to transmit signal into the system. By increasing or decreasing the temperature, information can be sent into the chip. The response from the chip we can get retrieved from standard I/O. For this case, we got this from the DVI. And of course, it can be easily embedded in IP core as a bidirectional side channels, and it did not occupy big area for our mechanism. So it's good for the either positive or negative applications. And here I want to talk about our second approach, that's using timing modulation. By changing this is what we did for, this is actually if you see that, this is the memory module. And then we build this on top, and we can plug the capacitance onto it, change the capacitance. So by changing the trace capacitance, we can change the DDR delay value, and then the information can be transmitted into the system. Of course, also the response can be received by the normal channels. So first is about DDR interface. I want to introduce DDR interface. DDR interface is consisted of clock, control address, and a bidirectional data bus. Timing is critical due to its high speed. For example, DDR2 533C data rate can be 533 megahertz, so it's fast. So the phase adjustment is required because the PCB-related trace delays, the thermal control the propagation delay we just saw in the first approach. By changing the temperature, actually the frequency changed and the propagation will be changed. Propagation delay will be changed. And also the process-related propagation delay on both the memory side and the FPGA side. So the I delay is introduced in the DDR controller. So how does the I delay work? First, we need to know that control signals on the DDR can be broken into the chip select, row address strobe, and column address strobe, write enable, data strobe, byte write enable, a few other signals. And the data strobe is dominate the clock, the information about the data. That's on the data is transmitted on the DQ. So if we change the trace delay, if we change the we put the capacitance on the trace, we actually change the trace delay. And if we change the trace delay, then the I delay will get changed to adjust this phase. And then the information will be transmitted in. So here is how it works. If we put the capacitance here, then we will get the I delay being adjusted in order to make the sample point of the IDDR take place in the middle of the data valid window. Then we will see that that DQS is being shifted in order to make the FPGA clock sample at the middle. And also the DQ I delay is equals to the DQS I delay plus the arbitrary number. It's in our case we set as the half of the bit period. And this is the block diagram. And we see that all the rest is actually based on Ray Bittner's paper, and we put the mechanism here. That's our mechanism. If the I delay gets changed, and if it's less than the nominal value, then we will set it as 1. And if it's bigger than the nominal value, we'll set as 0 to trigger our embedded circuit. So based on this, we put on the capacitance, or we remove the capacitance, or maybe we can put the negative capacitance. We can send the information into the circuit. And this is the testing setup. The tester code is modified based on arrays code, DDR2 IP core. It can be downloaded from the research.microsoft.com. And it has the 8 bits per DQS setup and 8 DQS groups totally. Because the DQS 0, 1, 2, 4, 6, they are located at the top side of the DDR module. So we tested them because it's easy for us to set up and evaluate. And we measure the ideal value under the following attaching capacitance. First is the nominal. We did not put anything, only the tester bench to test it, get the nominal value. And then we tested 10 pico, and 12 pico, 15 pico, 22 pico, and 47 pico. We select these values because these are the values we can get as a discrete ceramic capacitance. And here is the testing results. So the yellow line, yellow highlight shows the nominal value. MX stands for the maximum, AV stands for the average, MN stands for the minimum. And on this column shows how much capacitance we put. And the red word with the cross line means these are invalid measurement results. So we need to ignore them. But on the lower parts, I plotted these data in the graphs. And if we see that, we can see that it's consistent trend for all the DQS that we tested. With the nominal value, it's highest, and then it's with the capacitance we put on, it's getting lower and lower. And finally, it's hitting the invalid data, then it's jumped to here. So this proved that we can send the information into the system by changing the capacitance. And the bandwidth, practically 8 bits can be transmitted into the FPGA simultaneously through 8 DQS signal traces. And ideally, the resolution for each DQS ideally can be 64. And the dynamic range can be 64 to the power 8. But in reality, we tried it. It doesn't work in that way. And we can get 16 DQS ideally values. This is the equivalent to 4 bits. And the jump rate can be 200 megahertz per 5 cycles per calibration, which is equivalent to 40 megahertz. So from this, we can get our estimated maximum bandwidth to be 1.2 gigabits per second. But we will demo this approach for just 5 kilobits per second. Because the jump rate, we suppose we can get 1 kilohertz, and actually in the demo maybe a little bit lower. And the modulation is 1 bit, and the channel we can get is 5. Okay, so here is the demo. I have the capacitance. That's the ceramic capacitance. It's 12 pico. And if you see that, I have my memory plugged here. It's exactly the same as the picture. I took the picture here. And now it's setting actually at the DQS 0. So if I plug this one onto DQS 0, that should be here, you will see the picture changed. The picture changed from the lock into unlock to be open system. And if I remove it, get it back. So from this, we proved that we demonstrated and we proved that this capacitance-related I delay can work. And it also can be bidirectional side channels communication. And modulation can be done on every DQS signal traces. And the estimated bandwidth can be 1.2 gigabits per second. And here I showed a picture about how to make the modulation. We can use the varactor, or we also can use those capacitance array. And the last is about I/O pin hijacking. This is the setup for the I/O pin hijacking. The idea is sending the information into the system and receiving information from the system by the I2C interface built into any memory modules. And here I using just one FPGA board. So I have this is the memory actually, and that's the I2C interface. And I use another GPIO to mimic another I2C interface and connected them together to demo this application. So first, the introduction about this is every DDR module contains an EEPROM, which provides vital information such as the speed and access time, and the number and organization of the chips, special features such as faster random access, and it's programmed by the module supplier. So system BIOS only read this SPD information when it's at the boot time. After it gets all the information, it will keep this interface between the memory module and the system working at the optimum condition. And the JEDEC standard also described this as this SPD mechanism as required and standard in the memory module. And its interface is using I2C. So we know I2C is a bidirectional interface. If we have known this SPD mechanisms, and the memory module will work in the system only for the very conservative condition. So maybe like for DDR2, we only can, without the SPD information, it might just working as DDR. So the implementation is in this way. First, the FPGA is a victim on the right side. On the left side, it's when it's boot up, it's talked with the memory module. The memory module has the I2C slave with the designated device address. That's common for every EEPROM on the memory module. And the FPGA, as an I2C master, get the information about SPD. Then it will configure the interface between the FPGA and the memory module. Then it released this interface. So this interface is no longer being used anymore. So in this case, we changed this FPGA from the I2C master to the I2C slave, and assign the designated address. It can be any value, just randomly choose. And then if we have an attacker or we have an external system wants to talk with the system, we can reuse these two wires to simulate another I2C interface by using our external system as I2C master. The interface does not necessary to be I2C. This is the benefit, because here we just simulate as I2C, but it can be like RS-232 or any other interface that requires only two wires or even just one wire. And the bandwidth, the small I2C has a very small overhead. if you're sending a lot of data, it's only requires 7 bits for the slave address and 8 bits for the register address. And also, after sending every data byte, you have the acknowledge and not acknowledge. It's only 1 bit. So it can send unlimited data byte transmission capability. And I2C speed can be 100K bits per second, 400K bits per second, 1 megabits per second, 3.4 megabits per second. Achievable highest data rate depends on the detail hardware. It mostly depends on the trace and your design. And the bandwidth for based on this, on the bandwidth for the estimated maximum, we say it can go close to 3.4 megabits per second. And we will demo is for just 100 kilobits per second, because we set the I2C interface working at 100 kilobits per second. So this is the demo. I have the information set should on the dip switch 1. If it's off, this will show in lock. And if this one is on, this will show in the open. So now it's off. And if I set this one to on and then send it, then it will open. And if I want to lock it, I just set this to 0 and send it through this I2C. It's getting locked. So that's the demo. And the conclusion is, with the SPD mechanism, information can be transmitted and received between the system and outside without any limitation. And the embedded circuit only responds once the designated device address is called. So for the negative application, like attacker, it's hardly to be detected, because it's not always on. It's always standby, waiting for the address to be called. And the mechanism can be any 2-wire or 1-wire interface, not limited to I2C. Like what I said previous, like RS-232. And the maximum bandwidth can be 3.4 megabits per second if using I2C. And the high data rate can be achieved. For example, RS-232, as recorded, is 11 gigabits per second. But all this, of course, depends on the detail layout. Okay, now this is the conclusion for the presentation. So we proposed 3 approaches of the side channels. And we designed, implemented, and demonstrated. For all these 3, bidirectional communication is achievable. And the bandwidth can be pretty high. And the embedded circuit can be triggered externally through these channels, but not always on. This is very applicable, very feasible for the negative applications. And the approach are feasible for positive or negative applications. And our future work, further investigation on the modulation scheme to increase the bandwidth. We still need working on that. And also the possibility of the hybrid system by combining these 3 to 1 to increase the bandwidth. And also we needed to analyze on the risk and the cost on these approaches. And this is the references. That's all for my presentation. Thank you.
Question?
Yeah.
When you were talking about the bandwidth on the thermal changes, it would seem like you can't vary the temperature that quickly. And
Yeah,
so it would seem like it would be hard to get that much data in.
This is our ideal estimated maximum bandwidth, because we think we can design some hardware can change the temperature very quickly and very efficient and accurate.
I would think just the insulation in the case
Yeah.
It would slow down the propagation of the temperature change from the outside.
Yeah,
of the
but
chip
this
to
is
the
all
inside.
depends on your feedback system. If you have a very stable, very fast response for your second order feedback system, you can change that very quickly without a problem. But of course, we haven't done that. This is just our ideal maximum bandwidth.
So those calculations were done assuming that actually the thermal change. So for example, if you opened the package, and you actually had access to the bare die,
Yep.
then you could attach something that would be able to change the temperature very, very quickly. The only, and basically, if that wasn't the limiting factor, if basically how there's a certain amount of time that was required in order to sense what temperature it's basically, because you have to count a certain amount of time such that you know that any variance that is in the system will be able to account for that. So basically, you have to get over that kind of noise ratio. So if you count that as the limiting agent, then that's where those about 2 megabits per second.
Yeah.
So it's very optimistic.
Yeah,
It's very
You're
optimistic.
gonna have some thermal inertia in there. No matter what.
And absolutely. But I mean, basically, at some point, if you're willing to put the power of the sun contained in there to heat it up, and absolute zero on the other side, and somehow modulate between the two, that's it. And actually, the Peltier devices that we use, so basically they're current controlled temperature flipping devices. They respond very quickly. And it's just a function of how much current you're willing to put through.
And I could see you could get in hundreds of bits a second easily, which would be enough to send an ID or something.
Well, and for that matter, it's also how sensitive, how quickly you can change it. It depends on how accurately you want to change it.
Right.
So,
Are you loading those pictures from the slideshow off the DRAM? Or the DDR2?
yeah.
It's pretty impressive that you can stick a capacitor on the thing.
Yeah, and it
still
just
works.
continues to work. Well,
Yeah.
that's because these systems are built to be robust, right?
Yeah,
That's the
I
whole
guess so.
reason why they do the recalibration during runtime, is because they have to be robust, such that you can do things like shove the capacitor on it and it just keeps running.
A lot of them don't do that, including the Xilinx one. Well, mine's the only one that does it.
You know of.
If you do that to the Xilinx one, I don't
So
think
we're
it'll work
stress
so
testing
good.
the robustness of your implementation.
Yeah.
I think if you take the temperature between -40 and 102 up, the thing is shattered.
Well, so yeah, that's actually another thing, is that I was worried about the physical strains on the bonding and stuff like that, because if you change the temperature too much, you flex and flex, and then all of a sudden it breaks. But at least in the testing that we did, which honestly, actually, -15 is pretty cold. And positive 85 is really warm. I mean, we got frost on the chip. I mean,
Yeah.
we froze it solid, and didn't seem to be
No
a
problem.
Of course, tomorrow the thing
Yeah, I
will
was
break.
gonna
I don't know.
What's
But
the spec of the chip? Is what temperature range?
-40 to 100
Okay.
Operational?
operational.
Oh, okay.
Yeah.
So we're well within
Very
operational,
sorry.
but that's
But that
that's
doesn't mean you
static.
can switch.
Yeah, it's not meant to switch between.
That's also stated here. -40 to 100 plus 100. And also we haven't looked into the differential modulation. The differential modulation may be helpful increase the bandwidth as well.
The problem there is that there's an issue with encoding. So, for example, rather than fixing it to a particular temperature, if you just set it to increasing or decreasing a temperature, then that's good.
It's a lot more robust, yeah.
The problem is that you need to have an encoding system that has a guaranteed average zero temperature, right? Because if you have it, 1 is increasing temperature and 0 is decreasing temperature, what happens if you feed it a string of nothing but 1?
That's the standard non-return to zero.
Yeah,
encodings, right?
and that's the thing. So you need to have some encoding system that's guaranteed.
Or return to zero. encoding.
A guaranteed even number of zeros and ones. But unfortunately, that's a whole other problem. Now you start getting into information.
Right. But I mean, those things exist.
Yeah,
To do
absolutely,
that,
Yeah.
absolutely,
so-
yeah.
We
The
can
gray
just-
coding.
we can
I
ju-
feel like.
For
ju-
example.
We can just transfer that technology to here.
I wasn't clear on how the GPIO relates to the I2C, because you're playing with the GPIO pins there, right?
Oh, I just for the I2C, I only have the GPIO dip switch one
Who is
controller.
reading them?
I'm sorry.
Who reads the dip switches? Who reads them? FPGA?
FPGA, yeah.
Or isn't that displayed?
No, first is back to the slides.
I think it's either combined on one.
First is this one. This is when it's working at the master. But when it's going to be the slave, then this, actually these two systems I implemented on one FPGA.
Ah, okay.
Yeah, you just put
And,
all functions on one chip.
So I have this wire here that's showing on the,
So basically you're
that's showing on here. These are the attacker system. That's the going wire to the memory. Yeah.
Do you have any model as to what was going on when those, with the invalid statistics where they seemed to a little more than double? They had a little less than double, that would
Yeah, I was
have thought that it
wondering
was
what
missing every other count, but it,
So that's on the DDR timing.
Yeah, why were those, what made those invalid?
Yeah. But
Yeah,
this,
those-
right, yeah, the numbers that were in the 60s.
that's because it's getting to be too small and it's feedback and it's lose the synchronize. So it's getting to here. Because if talking about this one, it's by shifting this one to get aligned with this FPGA clock. And if it's getting shifted too much, it's actually lose the lock.
Right, when it loses the lock, I would expect that it would like catch it every other time, it would go up to about double. It is going up to about double, but it's going to a little more than double rather than a little less. I
Yeah.
was wondering if you had any model as to why the numbers came out in the range they did.
So that has to do with the fact that once you lose the synchronization, all bets are off.
And it's probably just noise or something.
That's what the calibration routine that's used. Essentially, when it doesn't know what to do, it just gives up and says, "Good luck." And so the window the window where you can actually capture valid data is fairly wide, so you can get lucky. And just by picking an arbitrary value, you may accidentally get correct data, which is, basically you don't break the system. But once you start shifting things so much that you're overcoming that and it can't do calibration, then basically it just gives up. In which case you could get any number.
Right.
So at that point, you're exceeding the physical limits of the system.
Yeah.
Like,
So
it's
the fact that
becoming
it seems
too slow.
consistently around the 63 range is probably some artifact of its attempt to figure out where it is.
I'm amazed you can include that extra little breadboard on there and it still works at all. That's pretty impressive.
Well, yeah, so that's a whole nother problem. So, like, all of this seems kind of clunky, but the issue is, like, so if you were James Bond and you had, the resources of M5 at your disposal, whether you could make this kind of, a module that you can kind of hide in your pocket and just kind of attach this thing while you're walking past, where it's actually it actually looks like it and acts like it's part of the DDR module itself. And that's really easy, actually. I mean,
Well,
with the very crude tools that we had at our disposal.
Well, and you have to plant the software in there that'll do something with it.
Well, right, but that's a different issue.
Right?
Right?
That's the model is you send the chip to get made in wherever, right? Like China or Taiwan or something, and they put a little IP core in there as part of the manufacturing process, and then over here somebody can put their little chip in the DDR and you can never find it.
Right.
I guess that would be the.
Or if you find it, it's too late because whatever secrets that were inside the box are now out the line.
Already gone, yeah.
Cool. Have you investigated any way to export data out from the system without using the GPIO at all? Like, for instance, say there's a malicious manufacturer who puts their own IP core and lets them receive data through like the thermal channel, and then could they also send data from the thermal channel so that they could, like, for instance, find ATMs that have custom chips on them in the field and then put like a small device on it that sends a command to get, you know, the last few pin numbers out of it, but then leave the system in place without needing to modify it? Or do you think that
Yes, for the thermal, actually, I did not use any GPIO. So
Well, I think what he's saying is they're using DVI as a physical pin.
Yeah, can you, I mean, conceptually, you could modulate the temperature of the chip back out, right? Send the information out that way or something like that. Is more what he's asking, I guess.
So the concept of a side channel transmission is actually fairly well documented. So that's why where people start doing, you know, differential power analysis and stuff like that. So we felt that at least when we started this back 12 weeks ago, we felt, okay, well, that's been done. What hasn't been done is actually building a receiver, because in general, building a transmitter is easier than building a receiver.
Yeah.
And so that was kind of the challenge that with the G was, okay, so people have done side channel transmission. Let's see if we can do side channel receiver. So the answer is yes.
Very cool.
One example, right, is actually using like DDR or FPGA, you change the image slightly such that it has sharper edges, and that makes the signal leak out of the cable in a predictable way, and you can pick it up across the room, or just by changing your algorithm so that it does more cache misses in a certain time, then you can analyze the electrical radiation is measurably different.
Okay.
Stuff like that.
But you're right, though, in as much as, for example, if you walk up to an ATM and you do something to it such that it triggers this thing inside, what's saying that you couldn't?
Right.
You're inside the system at this point, right? So what says that it couldn't just display those pin numbers to the screen that it's already connected to?
Yeah.
But yeah, I mean, the idea is kind of hidden transmission and hidden receiving is sort of is an interesting thing. That's kind of something that we're looking for future work.
A cute hack you could do is to make the picture be a picture of a thermometer. So it
Oh,
actually shows
yeah.
the temperature
Yeah.
going up and down.
yeah.
So what's the last story on the antenna transmission?
That one we try to implement, but just don't have time.
What was the goal on that?
Because we're in the case that the paper claims that they're doing it one way. Right.
Yeah.
So what Sandra is referring to is that there was a paper, actually that paper that image is from with the ring
wire,
antenna,
yeah.
Right.
that claims that what they're actually picking up is RF signals that are emanating off the chip. But we did the calculations and we consulted with some of the RF guys here, and basically they said that there's no way that the FPGA can generate a radio frequency that's high enough that could be transmitted with any reasonable amount of power, with any basically non-zero power out of anything that's attached to it. So you need an antenna that's inches long.
Yeah, well, but that's any of the traces on the breadboard, right?
That's the point. They thought it was coming from the chip.
Right.
It's not coming from
It's
the
coming
chip.
from
It's coming
anywhere.
from the
Right.
board.
Right.
And for that matter, so in that paper, basically they set this thing up and then they say, okay, something happens. They have this antenna and they hook it up to a scope and they say, well, okay, something's changing when we do this.
Right.
The question is, what is changing? What's changing is actually the EM, electromagnetic capabilities of it. So they're, for example, we even looked at this. So if you put a loop in and you tried to send a current through, right? Can you sense that current? And again, the RF and the antennas guys here said, basically the loop that you can make is not large enough to couple.
Okay.
So what these guys are actually picking up is probably the current coming through the power pins.
Yeah, I was going to say that would be my guess too.
So that basically you can put something that has very high power consumption and very low power consumption, and then modulate that. But that's kind of that's a different phenomenon. Essentially, at that point, just throw away the EM and just put a voltmeter on it or a current meter on it. That's a lot easier.
Yeah.
They actually, I guess it was more or less power, right? But that's one of the ways that they claimed you could break some of the AES decryption algorithms, right, on the PCs,
Yeah,
measuring
that's
the
right.
power difference between different stages of it.
Yeah, that's right. Or the noise in this case, right? So like, as the power supply works slightly harder or
Right, it
slightly
makes more or less
less
noise.
hard,
Yeah.
it basically it modulates the high frequency noise that comes out of it. And so that was one of the things. But I mean, basically, I think that these side channels, just in general, are so they're not very well understood.
It sure seems like, though, if you had a little knowledge of how your chip was going to be used on the actual system, you could pick a particularly long trace and make like an AM radio transmitter thing out of it pretty easily.
Again, it's just a matter of, so in theory,
It's not really
any
helpful, but-
current that you put down a wire, you get something out, right?
Right.
The problem is that whether or not it's anything above effective zero.
Right.
So it's non-zero, but it's so small that there's nothing, we can't build a receiver on the other side that they can pick up. So the real trick here, so originally, again, so this whole thing was started about side channel receiving.
Mhm.
My
You wanted to be
question
able to
was,
receive it, yeah.
was whether we could use, whether we could use a trace on the board and use that as a receiver. And basically the RF guys here said, no, not gonna happen.
I'm still not convinced you couldn't do that, considering how well that high-speed serial lines will couple with each other if you're not careful.
Well,
And you do know what the circuit look like. You do know the traces.
that's true,
They're not-
that's true,
no.
that's true. But at some point, it was also, if we're pumping that much energy into it, what else are we frying?
Well, that's
Besides
true, but-
just, basically, are we gonna create other problems? So yeah, if we create an EMP, never mind how we do that, yeah, the thing will notice, but
Right.
unfortunately, it'll be totally useless.
Yeah, I don't know, you could hit the sweet spot, I would think, maybe.
Right, yeah, that's the question, can we hit a sweet spot? But I think just in general, the idea being is that there's a lot of ways of sort of, we're trying to define kind of the fringe of what communication is possible, right? And we basically picked three points and said, okay, these are certainly within the realm of capability. You can demonstrate, you can do it,
Yeah.
it works. EM, as far as I'm concerned, the jury's still out. The theory says, not so much, but who knows, we might get lucky. But there was already so much on G's plate that I said, let's punt.
It's part 2.
I guess that's it.
Okay.
Yeah.
Kudos for a working demo on all 3, though.